6611 kV distribution substation design. Abstract: over the decades, electricity demand has increased considerably. Electric energy is produced in power plants that are located far away from consumers. It is given for consumption through a vast network of transmission and distribution lines. In many places on the power grid, it may be desirable and necessary to modify some features of the power supply. This is accomplished by a suitable device assembly called a substation. Some characteristics of the power supply include voltage level, power factor, frequency, AC to DC, etc. are included. It is a major challenge to design such a modern complex structure keeping in mind all the design parameters. Keywords: substation design, AutoCAD design, earthing. Introduction. Substations are an important part of the electrical system. The continuity of supply depends to a large extent on the proper functioning of substations. Therefore, it is important to take great care while constructing substation and designing. Important points to keep in mind while planning the substation are as follows. It should be located at the appropriate site. If possible, it should be located near the load center. It should provide a safe and reliable system. For safety reasons, compliance with regulatory authorities is required to be taken into account. It should be easy to use and maintain. This should include a minimum capital cost. Bus bars are important components of substations. There are many repeated arrangements. A single bus bar diagram. B. There are simple bus bars. C. Main bus and transfer bar diagrams with sectioning diagrams. D. Double bus bar diagram. E. Diagram of main double bus and transfer bus. F. Half circuit breaker system. 2. Design of 66/11 kV substation. Before choosing the nominal values of different devices in the substation and deciding their location in the substation, it is necessary to draw a single line diagram, also called a key diagram. Fig. 1 SLD of 66 kV/11 kV substation. Here, the unique busbar arrangement with sectioning scheme is described in SLD. All images are created in AutoCAD software. Once the key diagram P is repaired, the configuration diagrams are drawn to show the actual state of each instrument's plan and section configuration. This provision will reveal the physical condition of each piece of equipment. Distance between different devices. Phase separation distance. Phase, land separation distance, horizontal. Ground clearance phase, vertical. Interconnection between lines of the same voltage level, this allows the stations to distribute the power of different lines. Change of electrical energy, processors can switch between voltage levels to another. Thus, we can classify MV/LV substations on the networks on which they are used as well as the tasks they complete. Prior knowledge is required to obtain MV/LV stations. Reference standard and regulator equipment, voltage, power quality, short circuit power, etc. Linked to specific usage requirements. Obstacles, installation, and environment, second. 311/0.433 kV substation. The decision on MV or LV supply will depend on local conditions and considerations such as those mentioned above, and will usually be imposed by the utility. When it has been decided to provide power to MT, there are two widely followed procedures. The electricity supplier builds a standard substation near the consumer's premises, but near the MV/LV transformer load center, the premises. Inside the transformer is located in the room. The consumer builds and furnishes his substation in his own premises, from which the electricity supplier makes MV connection. A choice of job site. The consumer has to provide some data for public service from the first phase of the project. Maximum expected power demand, kVA, site planning, and elevation indicate the location of the proposed substation, the degree of continuity of supply required from the information provided by the consumer, the electricity supplier should indicate. The type of supply proposed and defines the type of supply system, on a cable or underground network, a description of the service connection, service on a line, main ring installation or parallel feeder, and power limit, kVA, and fault current. Nominal voltage and nominal voltage, the highest voltage for the device, metering details that define the cost and tariff details of the connection to the power network, consumption and fixed costs. B. The request for approval should include the following information, broadly based on the above preliminary discussions. The location of the proposed post. Single line diagrams of power circuits and connections, as well as proposed earthing circuits. To establish all details of electrical equipment, including performance characteristics. Arrangement of equipment and measurement components. Provision to improve the power factor if necessary. Provision of an emergency power plant, MV or LV, if necessary. C46611 kV substations, the following minimum electrical and safety clearances are required. Nominal. Table 1.1. The design of the substation cannot be finalized without all selection, and the design calculations for the equipment to be performed should be postponed until different items have been ordered and dimensions are not obtained from equipment suppliers. Technical specification of general equipments. For earthing scheme design. The current earthing system in a substation takes the form of a grid or a mat consisting of several sections or rectangular traps of horizontally buried earthing conductors that are connected to multiple electrodes controlled at intervals. As shown in Fig. Fig 2 model of earthing grid. The purpose of the earthing system is to provide as much surface as possible under and around a station, at a uniform potential and on a potential ground as close to or as absolute as possible. Ensure that the most affected parameters for the design of earthing grids are fault current and duration, soil and surface resistivity in place of substation, soil structure and soil model, property and cross-section of material used for conductors of earth mat, geometry of grounding mats, area covered by ground mats, touch and phase capability allowed. The flow diagram and calculation sample for earthing is described above and below, in which all the required parameters are represented by the design of earthing mats of substation 66 kV. Design input data. Description. Notation. Unit. Symmetrical fault current in substation. IG. A. Duration of shock for determining allowable body current. TS. Seconds. Duration of fault current for sizing ground conductor. TC. Seconds. Surface layer resistivity. S. OM. Surface layer thickness. HS. M. Grid reference depth. H0. M. Soil resistivity. P. OM. Depth of ground grid conductors. H. M. Length of grid conductor in X direction. LX. M. Length of grid conductor in Y direction. Li. M. No of grid conductor in X direction. NX. NOS. No of grid conductor in Y direction. New York. NOS. Spacing between parallel conductors. D. M. Length of ground rod at each location. LR. M. Number of rods placed in area. NR. NOS. Decrement factor for determining IG. DF. Dash. Equivalent earthing mat area. A. M2. Total length of buried conductor equals LXX New York, plus, LX. NX, plus, LRX NR. L. M. Total length of ground rods. LR. M. Equivalent impedance ZEC. ZEC. O. Total length of conductor in horizontal grid. LC. M. Peripheral length of grid. LP. M. RMS current. I. Ca. Maximum allowable temperature. Tm. Degree C. Ambient temperature. Ta. Degree C. Reference temperature for material constants. Tr. Degree C. Thermal coefficient of resistivity. At 0 degrees Celsius. A 0. 1/degree C. Thermal coefficient of resistivity. At reference temperature Tr. Ar. 1/degree C. Resistivity of the ground. Conductor at reference temperature Tr. R. O.cm. 1/A0 or 1/AR, Tr. K0. Degree C. Duration of current. Tc. Seconds. Thermal capacity per unit volume. TCAP. J/cm superscript 3 degree C. Earthing grid conductor area. CS surface layer derating factor. This is tolerable touch voltage of grid considering 50 kg/person. This is tolerable step voltage of grid considering 50 kg people. Grid resistance. Typically, the site engineer specifies a grid resistance. Earth resistance should be as low as possible and should not exceed the following limits. Power stations 0.5. EHT substations -1.0. 66/11 kV stations -2.0. If the ground resistivity is 800 ohm or more, it will be difficult to obtain the desired low resistance of 1 to 2 ohm for a network station with a single grounding band. In such cases, it becomes necessary to increase the area of the grounding network. Simply increasing the amount of grounding tape may not help much to reduce the resistance of the grounding system, and the use of deeply driven rods may be unavoidable. Ground potential rise, GPR, equals, maximum grid current Ig * grid resistance Rg. Now compare GPRE touch tolerable voltage. If yes, then design is safe. If GPRE touch, then find estimated E mesh and E step. Estimated mesh voltage. Fig 3 earthing grid design. Estimated step voltage. Compare E mesh estimated E touch tolerable. If yes, then compare E step estimated E step tolerable. If yes, then design is safe. Otherwise, modify by increasing or decreasing spacing of conductor, length of conductors, or by increasing or decreasing number of rods, and calculate design parameter again. V. Conclusion 1. Substation design and equipments by P.S. Satnam and P.V. Gupta. 2. IEEE STD80 trademark -2013 on IEEE Guide for Safety in AC Substation Grounding. 3. IEEE STD 998 trademark -2012 on IEEE Guide for Direct Lightning Stroke Shielding of Substations. 4. Auto CAD software. 5. Case study on installation of OPGW cables for GetCo's 220 kV transmission line. 6. ASPABLA, Electrical Power Distribution System, Tata McGraw-Hill 5th Ditone. The Power Netvo RX will continue to grow and develop, so that the design of the substation evolves to meet the new requirements. The use of a grounding grid with specific spacing and the use of a lightning rod with shielding wire will reduce accidents and at the same time reduce post costs and protection against lightning strikes without affecting the safety of working personnel. Post respectively. Therefore, the goal of lower installation and assembly costs, the ability to extend future loads, safer operation, and easier maintenance, more reliability can be achieved with optimal design and performance. The substation can be improved.